Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. This is part 3 of the first chapter, the real number system, and the title is Lower Bounds and Infimum. Outline: lower bound of subsets of R, infimum of subsets of R, and examples of lower bounds and infimum of subsets of R. So again, as in the previous video, we have seen what are upper bounds and what are supremums. Okay, so lower bounds and infimum are exactly the opposites of upper bounds and supremum. Okay, so again, let me start with the same example that I had started with in the previous video. So let me take a set having 4 elements, a simple one. Okay, and let's make one observation here. This number 1, if you see, it is less than or equal to all the elements of the set A, right? So 1 is less than or equal to itself, 1 is less than or equal to 2, 1 is less than or equal to 3, and 1 is less than or equal to 4. So 1 is less than or equal to each and every element of the set A, right? Now why only 1? Anything which is less than 1 will also work. For example, I can pick up 0. 0 is less than or equal to x for every x in A, right? 0 is less than or equal to all of them. Again, if I pick up some negative number minus 5.678, say, even this one is less than or equal to x for every x in A. Okay, so such real numbers which are less than or equal to each and every element of a set are called lower bounds of that set. Okay, so this motivates this definition. So let me put it down: lower bounds. Okay, so let A be a subset of R. Okay, this be non-empty set. Okay, then a real number beta is called a lower bound of A. Okay, is called a lower bound of A if beta is less than or equal to each and every element from the set A. Okay, so if beta is less than or equal to x for all x in A. So if this happens, then beta is called a lower bound of the set A. Okay, so using quantifiers, how will I put this? Beta is a lower bound of A. So using quantifiers, I can write uh, every element of A is bigger than or equal to beta. So for all x in A, beta is less than or equal to x. Okay, so that's how you write this using quantifiers. Now geometrically, if you look at this, let me put it on a number line because that is the best way in which you can understand. And I will mark the set A on this number line. Okay, so supposing these are my points which I'm marking in red. Supposing those are the points in A. Okay, supposing these are my points in the set A. All right, so these are the points in A which are in red. Okay, so a number here beta which is less than or equal to all the members of the A is called a lower bound of A. So geometrically talking about lower bound should be on the left of each and every element of the set A. Okay, then only it will be less than or equal to each and every element of the set A. Okay, I hope that's clear. Now, when will I say that beta is not a lower bound of A? That means I'll have to negate this. Okay, so the negation of this would be what? I'll move to the next slide. So its negation is, you all already know what are negation. Its negation is there exists a point x in A such that x is or beta is strictly bigger than x, right? So there is a point in A, x, which is less than beta, then only beta will not be a lower bound. Okay, so when I say beta is not a lower bound of the set A, okay, so what should happen if and only if there is a point x in A, there is a point x in A such that x is less than beta, strictly less than beta. Okay, so that's the negation of the statement beta is a lower bound of E. Now, if you put this on the number line and if you mark your set A again, I'll do it in red. Okay, so supposing these points which I'm marking in red, okay, supposing these, this is my set A which is in red, okay, then if beta is not a lower bound of A, then beta should lie somewhere here, this side, okay, so it shouldn't be that side completely, maybe here, so that there are points of A which are less than beta. So in such a case, this is an example of a situation wherein beta is not a lower bound of A. Okay. So this is how you negate the statement beta is a lower bound of A, and you have it using quantifiers as well. All right. Now let me take one set A. Okay. Let A be equal to this set open interval 0 1. Okay, and this is all the real numbers which are strictly between 0 and 1. Okay, so you all are familiar with this set now, open interval 0 1, and we know that 0 is the lower bound of this. Okay, so I can list some lower bounds of this set. So 0 is a lower bound, right? And if you take any other number which is less than 0, like -1, -2, -5, or minus 10 raised to, all these numbers I can put, even this one. So all these are lower bounds for the set A. Okay, so this means if you have a lower bound for a set A, then every number which is less than that lower bound is also a lower bound of that set. Okay, so if you have one lower bound, then you can produce infinitely many lower bounds for a given set. All right, so I will put that in a remark. If beta is a lower bound of A, if beta is a lower bound of A, okay, and supposing beta dash is strictly less than beta. So if beta dash is a real number which is less than beta, then beta dash is also a lower bound of E. Okay, so this is also a lower bound of, okay. So if you have one lower bound, you can produce infinitely many lower bounds. Okay, I hope this is clear. So moving on to the next definition. In the last video, we had seen something called bounded sets which are bounded above. Okay, so in a similar way, we have sets which are bounded below also. So supposing I have a set A, a subset of R, which is a non-empty set. Okay, so let this be a non-empty set. Then this set A is said to be bounded below. Okay, this set A is said to be bounded below said to be bounded below. Okay, I'll just rewrite it. Is said to be bounded below if there exists a real number beta such that which is a lower bound of A. Okay. So if for a if you have a set A and you have a you can find a lower bound for that set, then that set is said to be bounded below in R. Okay, said to be bounded below in R. That's important. Bounded below in R. All right. So let me take some examples. No, before that, using quantifiers, how will you put this? Okay, so using quantifiers, I have A is said to be bounded above, sorry, bounded below if there is a real number beta. If there exists a real number beta such that for all points x in A, okay, for all points x in A, beta is less than or equal to x. Okay, and this is nothing but beta is the lower bound of A. Using quantifiers, if you see, so there exists a real number beta such that beta is the lower bound of A. That's what it says. Okay, and if you want to say that A is not bounded below, then its negation would be A is not bounded below. Okay, this is going to happen if and only if you negate this. So no matter what beta you take, for every real number beta, I can find a point x in A such that beta is bigger than x. That means no matter what real number you take, that real number will never be a lower bound of A. And that's when you say that a set A is not bounded below. Okay. So let us look at some examples of sets which are bounded below. Okay. If you look at the open interval 0, 1, okay, if you look at this, then we know that clearly 0 is a lower bound of A. Okay, so 0 is a lower bound of A, and therefore this set A is bounded below, right? Again, if you look at the set of naturals, that is all your natural numbers 1, 2, 3, and so on. Again, 1 is the lower bound here, and hence this set of natural numbers is bounded below. Okay. One more example, the set of integers. So the third example is the set of integers. So if you look at this, this is nothing but all these numbers on this side of the 0 and all these numbers on this side of the 0. Okay, this set is not bounded below. Okay, this set is not bounded below. Why this set is not bounded below? So if you try to put it on the number line 0, -1, -2, if you tell me that this number which I'm marking here right now is a lower bound, then I can always find integers on its left, right? Because integers are infinitely many in numbers, even the negative integers. So I will get the so many integers here which are less than beta. Okay, so this set of integers z has no lower bounds. Okay, so this is an example of a set which is not bounded below. So z integers is not bounded below. Okay, and it is not bounded above also. Okay, this is not bounded above as well, because same thing, same reasoning will work on the other side as well. All right, now let me look at the same set which I already mentioned in the previous slides. Let A be equal to the open interval 0, 1, all the real numbers which are strictly between 0 and 1. Okay, and if I try to plot that here, let's say 0 is here and 1 is here. Okay, we said that 0 is the lower bound of this set A. Okay, 0 is the lower bound of this set A. Can there be any real number which is bigger than 0 and lower bound of A? That is the question now. Okay, so 0 is a lower bound, -1 is a lower bound, -2 is a lower bound. All the negative numbers, all the numbers which are less than 0 are lower bounds. Okay, now my question is, which is the greatest lower bound that you can have here? Can there be a lower bound which is bigger than 0? If so, then it will be somewhere here. And this here number here which I'm marking, this cannot be a lower bound because there will be points here which will be less than beta. So beta will not be a lower bound, right? So I can see that 0 is the greatest lower bound out of all the lower bounds that are existing for this particular set. All right. So that motivates the next definition of greatest lower bound, or what we call as infimum. Okay. Infimum, or the greatest lower bound, also written as GLB. Okay, greatest lower bound. Greatest lower bound. Okay, in the previous video we had supremum and least upper bound, and this is the greatest lower bound. Okay, so let's define this. Supposing I have non-empty subset of R which is bounded below. Okay, let A be a subset of R, be non-empty. Okay, then a real number beta is called, and infimum or the greatest lower bound of A if these two conditions are satisfied. So from the name itself you can guess the two conditions. I want it to be a greatest lower bound, so it has to be a lower bound first, right? It has to be a lower bound first, and it has to be greater than all the other lower bounds, then only it will be the greatest lower bound. So from the name itself it's clear what it should be. Okay, so the number beta is a lower bound of E. This is the first condition that is required. Okay, the number beta is a lower bound of E, right? The second condition is if you take any other lower bound. Okay, so if say beta 1 is any other lower bound of A, if beta 1 is any other lower bound of A, okay, then I want beta to be greatest lower bound. So if I pick up any other lower bound beta 1, then beta 1 must be less than or equal to beta. Then only beta will be the greatest one. Okay. So if you have understood the concept of supremum in the last video, this shouldn't be difficult, right? So beta, number beta is called the infimum of the set A if beta is the lower bound of the set A, and if beta 1 is any other lower bound, if you pick up any other lower bound, then that will be less than or equal to beta. Okay, so if you are able to show these two things for beta, then you can say that beta is the infimum of the set A. All right, now let's look at some examples of sets, and we'll try to find the infimum of these sets. Okay, so find the infimum of the following sets. Find the infimum. Sometimes it is also written as INF, infimum, or I have greatest lower bound also of the following sets. Okay, so the first one is the same one I'll pick up, 1, 2, 3, 4, which I had used in the first slide. Okay, now I want to find the infimum of the set A. So 1 is the lower bound because 1 is less than or equal to every element. So 1 is less than or equal to x for every x in A, and therefore 1 is a lower bound of A. Okay, so that's clear. Now what I have to prove? I have to start with another lower bound, and I have to show that another lower bound which I am taking, that is less than or equal to 1. Okay, so let's say theta be any other lower bound of A. Let theta be any other lower bound of A. Okay. Now, because theta is a lower bound, theta will be less than or equal to all the elements of the set A. Correct? So, theta is less than or equal to x for every x in A. And in particular, 1 is also an element in A. Right? So, in particular, 1 is also an element in A, and theta is less than or equal to all the elements of A. So, theta must be less than or equal to 1. So, what did we do here? In the first step, I showed that 1 is the lower bound of A, and in the second one, we showed that if theta is any other lower bound of A, then theta must be less than or equal to 1. That means any other lower bound of A has to be less than or equal to 1, and hence the greatest lower bound of A is 1. Okay. I hope this is understood by all of you all. Now, let's look at one more example. Uh, Supposing I have the set B, which is the closed interval 0, 1. Okay. This is defined as the set of all real numbers such that 0 is less than or equal to x and less than or equal to 1. So 0 is there, 1 is there, and all the numbers between 0 and 1 are also there. Okay. So this is the set on the number line. Now, the way the set is defined, from that it is clear that 0 is less than or equal to x, correct? For every x, then only that point x will come in the set B. So first, you notice that 0 is less than or equal to x for every x in B. Okay, that means 0 is the lower bound of B. So 0 is the lower bound of B. Okay, now what I have to show? 0 is the greatest lower bound. Okay, so the second step is what? I'll pick up any other lower bound. So let some notation, let's say theta or eta, say let eta be any other lower bound of A, sorry, B. Okay, let eta be any other lower bound of B. So because this eta is a lower bound of B, it will be less than or equal to each and every element of the set B. So eta will be less than or equal to x for every x in B. In particular, 0 is also a point in B because 0 is included here. X can be 0, right? The definition says x must be bigger than or equal to 0. So x can be 0. So in particular, I have, in particular, uh, 0 is a point in B and eta is less than or equal to all the elements of B. So in particular, it is less than or equal to 0. So what did we do here? In the first step, we showed that 0 is a lower bound, and if eta is any other lower bound, then eta must be less than or equal to 0. That means you cannot have any other lower bound which is bigger than 0, and hence 0 is the greatest lower bound of A. Okay, or I can write it as 0 is the infimum of the set A. Okay, I hope this is clear. If there are any questions, you can post it in the comments and I'll definitely answer them. Okay, now one more set, the set of naturals. 1, 2, 3, 4, 5, and so on. All these are naturals. Clearly, 1 is a lower bound. Okay. So 1 is less than or equal to x for all natural numbers n. So 1 is a lower bound of n. Okay. Now you pick up any other lower bound. Let sigma, say this is sigma. This is called sigma. Let sigma be any other lower bound. Same procedure. Okay, let sigma be any other lower bound, right? So that means sigma is less than or equal to x for all the natural numbers. In particular, 1 is a natural number, and therefore sigma is less than or equal to 1, and therefore 1 is infimum of the set A, of the set of natural numbers, sorry, of n. Okay, and this set of natural numbers, it does not have any supremum. Okay, that we saw in the last video. I hope these things are clear to you all. Let me do this property of uniqueness, which I done for supremum, that also holds for infimum. Okay, so let A be a non-empty subset of R. So let this set be non-empty. Okay, and let A be bounded below. Okay, let A be bounded below. That means it will have bounded below. That means it will have a lower bound. Okay, so I'll pick up two lower bounds. Let alpha and beta be lower bounds of, sorry, greatest lower bounds of A. Okay, then we have to show that alpha is equal to beta. Okay, so in one line, if I want to put this, I can say infimum of any non-empty subset of R which is bounded below is unique. Okay, so a set can have only one infimum. It cannot have more than one infimums. Okay, so what is given to me? Alpha and beta are greatest lower bounds. That means they are infimums. Okay, so alpha is given to be the infimum of A, and beta is also given to be infimum of A. Okay, infimum or GLB of A also you can put if you wish. I'll put both. You can use any one. Okay. Now alpha is the greatest lower bound of A. That means it's a lower bound. First thing, it is the greatest of all the lower bounds. Second thing, again beta is a GLB of A. That means beta is the lower bound and beta is the greatest lower bound. Okay. So it will work the same way that it had worked in the previous video. Okay, for the supremums. So I will assume that alpha is the greatest lower bound. So alpha is the greatest lower bound of A, and beta is also greatest lower bound of A, but before that it's a lower bound also. So I'll assume the lower bound property of beta. Okay, and beta is a lower bound of A. Now beta is a lower bound of A, and alpha is the greatest of all the lower bounds, and beta is any other lower bound. That means beta must be less than or equal to alpha, right? Because alpha is the greatest of all the lower bounds and beta is another lower bound. Also, you can reverse their roles now. Alpha is the lower bound of A. Alpha is the lower bound of A, and beta is the greatest lower bound of A. Okay, beta is the greatest lower bound of A. So what this says, beta is the greatest of all the lower bounds and alpha is the lower bound, right? That means beta must be bigger than or equal to alpha, or alpha is less than or equal to beta. And by the property which I had done in the first video of this course, if A is less than or equal to B and B is less than or equal to A, then both A and B are same. Okay, so by 1 and 2 we have alpha is equal to beta. Hence infimum of a set, if it exists, is a unique number. Okay, these are my references. Thank you.